Welcome to the deep dive. Today we're tackling this really big idea, permanent information storage.
Yeah, permanent. It's a huge concept.
Right. And how this protocol, Arweave, is trying to make that a reality. I mean, think about the internet's short memory.
Oh, yeah. Links break, platforms vanish, data just poof, gone.
Exactly. Arweave steps in with this vision to fix that, and also tackling those concerns around censorship, right?
Precisely. And to really get a handle on how they're doing it, we're diving deep into the core Arweave white paper, the blueprint, basically. Yeah, it lays out all the technical stuff, the design principles. Specifically, this is based on version 2.7.0 of the protocol.
Gotcha. So your mission, listener, if you choose to accept it, is to walk away from this understanding that, the fundamental concepts behind Arweave, how it actually aims to do this permanent, decentralized data storage thing.
And we're here to give you that shortcut, that key understanding without drowning in jargon.
Okay, let's unpack this. Where does the paper start?
Well, it kicks off acknowledging the internet's speed, its potential for transparency, which is amazing.
Sure.
But it immediately points out two massive hurdles Arweave is built to overcome. First, that thing we just mentioned, data loss. The internet just forgets things.
Oh, man, we've all hit that wall, right? Click an old link, 404 not found.
Ugh, the worst.
Yeah.
Like a digital black hole.
And the second issue?
Centralized control, which, can lead to information being censored, manipulated, all that stuff.
Big problems. So Arweave presents itself as the antidote.
Pretty much, yeah. A protocol for moving information across time and space, crucially without middleman.
Still intermediated, as they say.
Exactly. The ambition is, well, it's huge. A permanent, infinitely scalable record. For anything, no single point of control.
Okay, permanent is doing a lot of heavy lifting there. How do they even define that, let alone achieve it?
It is a powerful word.
Yeah.
And the paper actually pauses to look at dictionary definitions. Oxford, Merriam-Webster.
Really? What do they say?
The usual suspects. Lasting indefinitely, remaining unchanged. For Arweave, the engineering goal is stark. Store data for the maximum possible term, without change.
Maximum possible term. Okay, that's ambitious. Setting the bar high.
Very high.
So, okay, ambitious goal. What are the core building blocks? How does it actually function?
Right. It boils down to three fundamental components. First up, cryptographic proofs of storage.
Proving you have the data.
Yes, but the clever bit is doing it efficiently. Minimal compute power, minimal bandwidth needed.
Why is efficiency so key there?
Because if it takes massive resources, only a few big players can participate, right?
Yeah.
Efficiency maximizes decentralization, keeps it open.
Ah, makes sense. Okay, component number 2.
That's the storage endowment. Think of it like a built-in savings account, maybe.
For data.
Sort of. It's a self-executing financial mechanism designed to pay for long-term storage. And it cleverly leverages the fact that tech, especially storage, tends to get cheaper over time.
Interesting. So the idea is you pay up front, that goes into this endowment, which then drip feeds payments for storage costs way down the line, using less money because storage is cheaper.
You got it. That's the core economic idea.
Clever. Okay, and the third piece.
The third critical piece is incentivized evolution. This is really forward-thinking stuff.
Evolution. How does permanent storage evolve?
It's a way for the protocol itself to adapt and improve over time. But crucially, upgrades aren't forced by some central company.
Ah.
They're driven by community incentives, rewards for innovation, all while, and this is key, preserving user rights.
So more like community-driven upgrades, not top-down mandates.
That's the heart of it, and the paper really emphasizes this. The whole protocol. It's codified, open source, immutable in its current version. Totally transparent.
Giving users predictability, trust.
Exactly. Something hard to get with closed, centralized systems.
Okay, 3 pillars. Proofs, endowment, evolution. Let's dig into the protocol design itself. Decentralized consensus gets mentioned. Why is that foundational here?
Oh, it's absolutely crucial in distributed computing. You need a way for all these separate computers to agree on the state of things, the history.
Even if some are unreliable or even trying to cheat the system.
Especially then. Bitcoin really cracked this with Nakamoto consensus, right? Proving you could get agreement in a totally permissionless environment where you can't trust everyone.
Right, establishing trust without a central bank or authority. How does Arweave build on that?
It definitely takes inspiration from Bitcoin's proof of work. But they adapt it specifically to incentivize permanent data storage, not just computation.
Okay, how does that work in practice? The network itself.
So picture this global network of nodes, computers, right? Each one storing multiple copies of the data people upload.
Redundancy.
Yep. When you want to store something, you make that one-time payment to the endowment we talked about, and you send your data out to these nodes.
And then how does the network agree, okay, this new data is officially part of the permanent record?
Periodically, like every couple of minutes, one node will successfully mine a new block.
Like Bitcoin mining?
Similar concept, yeah. This block contains a batch of new transactions. Could be new data getting stored, could be transfers of AR, the native currency.
Okay.
This mining process is competitive, and it serves two main jobs. One, adding new data to the network. Two, verifying that the data uploaded previously is still being stored correctly.
Ah, the ongoing proof part.
Exactly. And as part of mining, nodes are actively pulling data from others, replicating it, especially after a block confirms new data exists.
So it's this continuous cycle, add new, verify old, replicate. Got it. The paper also talks about core design principles. What's the philosophy behind Arweave?
Yeah, two really stand out. First is minimalism.
Keep it simple.
Pretty much. Stick to a straightforward design, use cryptographic tools that are well-tested, well-understood.
Yeah.
The idea is this helps build broad social consensus and trust.
Makes sense. Complexity can hide bugs or be hard to grasp. And the second principle?
Optimization through incentives. This is really core Arweave thinking.
Yeah.
Instead of the protocol strictly dictating exactly how nodes must behave, it sets up economic incentives that encourage the right behavior.
Like reward good actions, penalize bad ones?
Sort of, yeah. It lets the participants figure out the most efficient ways to achieve the desired outcomes, allowing the system to evolve organically.
Set the rules, let the players optimize their strategy within those rules.
You got it. And because of this focus, Arweave really hones in on that one core challenge: permanent, scalable data storage.
Leaving the layer above it free for other things.
Exactly. The application layer on top is super flexible. That's why we're already seeing decentralized smart contracts, databases, all sorts of apps being built on Arweave.
And the paper also stresses that it's relatively easy to participate, low hardware requirements.
Yeah, it emphasizes the hardware and bandwidth needs are comparable to running, say, a Bitcoin node, which is pretty accessible for many.
That's crucial for keeping it decentralized, right? More participants.
Absolutely. Maximize participation.
They even use Bitcoin's history as a case study for incentive power, don't they?
They do. Pointing to the insane explosion in Bitcoin mining hardware efficiency, like 10 to the power of 13 improvements since 2011, blowing past Moore's law.
And costs plummeted.
Factor of 1,000,000 reduction, all driven by those mining incentives. Arweave argues it's using that same powerful principle, but directing it towards optimizing proofs of storage and efficient data routing.
Fascinating. Okay, let's brace ourselves and dive into the real technical meat. Cryptographic proofs of storage technical deep dive. First up, the block index. What is that exactly?
Okay, deep breath. Think of the block index as the spine of Arweave's data structure. It's a constantly growing, securely linked list of all the blocks ever added.
Like a master ledger index?
Kinda, yeah. Technically, it's a Merkleized list. Uses Merkle trees to summarize everything compactly. Each entry notes the block's hash, the total size of all Arweave data up to that point, the size, and a summary of the transactions in that block.
The transaction root.
Exactly. And this whole list is itself structured as a Merkle tree. The really neat part: each new block embeds the Merkle root of the previous block index.
Chaining them together cryptographically.
Right, which means if you verify the latest state of the network, which is quick, using something called an SPV proof, you can be mathematically certain about the validity of any block way back in history, without rechecking everything in between.
That sounds way more efficient than just replaying the whole chain.
It is. Big advantage.
Okay, next. Merkleization of data. How does my file get processed when I upload it?
Right, so you upload your data. First, the protocol chops it into standard 256 kilobyte chunks.
Fixed to size chunks.
Yep. Then for your data chunks, it builds a Merkle tree. The top hash of that tree, the data root, is what actually goes into an Arweave transaction.
So the transaction doesn't contain the whole file, just this root hash representing it.
Precisely. You sign that transaction with your key, send it off to the network.
Got it.
Now, within each block that gets mined, there's another Merkle root called the transaction root. This summarizes all the individual data roots from all the storage transactions included in that specific block.
Okay, layers of Merkle trees.
You're getting it.
Yeah.
And that transaction root then becomes part of the entry in the main block index we just talked about. The result is this massive, ever-expanding Merkle tree structure encompassing all the data ever stored, all linked chronologically and securely.
Wow. Okay. Merkle trees are doing some serious work here. Now, the paper mentions succinct proofs of access, SPOA. What problem are they solving?
SPOA lets someone prove they're storing a specific piece of data at a specific location within that giant Arweave Merkle structure.
Okay, prove you have chunk X.
Right. But the key word is succinct. The proof itself is tiny, and verifying it is super fast no matter how mind-bogglingly huge the total Arweave dataset gets.
So I can prove I have one tiny piece of a continent-sized library without sending the whole library.
Excellent analogy. That's exactly it.
How does the proof actually work, like between two nodes?
The paper frames it as a little challenge response game. Let's say Bob wants to check if Alice has a specific byte.
Bob's the verifier, Alice the prover.
Yep. Bob sends Alice a challenge offset, basically the address of the byte he's curious about.
Okay.
Alice finds the 256 KB chunk containing that byte in her stored data. Then she constructs the Merkle proof. This isn't the whole tree, just the specific pass the sequence of hashes needed to connect that chunk all the way up to the known public root hash of the entire data set.
Like the specific branches leading from the leaf to the root.
Exactly. She sends that path plus the data chunk itself back to Bob.
And Bob can check it.
Yeah, Bob takes the chunk, hashes it, then uses the hashes from the path Alice sent, step by step, recalculating his way up the tree. If his final calculation matches the known public root hash,
then he knows Alice has that chunk.
with cryptographic certainty.
That does sound efficient. What about the complexity? The paper mentions O log n.
Right, that's computer science talk for how the proof size and verification timescale as the dataset size n grows. O log n means it scales incredibly well.
Meaning?
Even if Arweave stored, like, literally all human knowledge, the proof for one specific chunk would still be manageably small and fast to check. The example they give is proving access within a dataset of 2 to the power of 256 bytes, which is astronomically huge, requires a proof that's only about 280 kilobytes.
Wow. That's tiny, relatively speaking. Okay, so we can prove access. But how does Arweave ensure miners store unique copies, prevent them from just storing popular stuff over and over?
Ah, yes, the replica uniqueness problem. Critical for actual redundancy if everyone stores the same popular cat video.
Not very resilient.
Exactly. Arweave tackles this with a process called packing.
Packing? Sounds like compression, but I guess not.
Not really compression. It uses a special computationally intensive hashing algorithm called RandomX.
RandomX, I've heard of that in connection with Monero.
That's the one. Designed to be memory hard. Anyway, Arweave uses it to transform a regular 256 KB data chunk into a unique packed chunk.
How does that make it unique?
The packing process itself involves significant computation by the miner. It takes things like the chunk's location, the current transaction route, and the miner's own address, feeds them into RandomX, and this generates unique cryptographic material used to essentially scramble or pack the original chunk data in a specific way.
So it costs compute power to create this packed chunk.
A fair amount, yes. And that's the key incentive. The idea is that the cost for a miner to repack a chunk on the fly every single time they need to provide a proof for it.
Should be more expensive than just storing the unique packed chunk they created earlier.
Precisely. It makes it economically rational to just store the unique packed versions you've already computed, rather than trying to fake it by packing duplicates on demand. The paper mentions a safety ratio around 19 at the time, ensuring storing is cheaper than repacking.
Clever economics. And RandomX itself, being memory hard, helps keep mining accessible to regular CPUs. Fights against specialized hardware dominating.
That's a major reason for choosing it. It resists specialized hardware like ASICs because it relies heavily on RAM access and randomized code execution. Helps maintain decentralization by leveling the playing field somewhat.
Okay, proofs of access, incentives for unique replicas. Now, what's this verifiable delay function, or VDF?
Right, VDF. Think of it as a cryptographic way to prove that a certain amount of real time has actually passed between two events.
Like a provable timer.
Essentially, yeah.
Yeah.
It's designed so it takes a specific number of sequential computational steps to calculate an output. You can't really speed it up much by throwing more parallel processors at it, but once you have the output, anyone can verify it very quickly.
How does Arweave use them?
They use a relatively simple VDF based on chain hashing. You take a starting value, a seed, and just hash it repeatedly using SHA-256, hash the result, hash that result, and so on.
Keep hashing.
For a specific number of iterations. If you know the final hash and how many steps were taken, you can be sure a minimum amount of time elapsed, assuming you know the maximum speed of one hash calculation.
And Arweave calls the output after a set number of hashes a checkpoint.
Yep. Generating checkpoints, say, for 1 second's worth of hashing proves at least 1 second of sequential computation happened. Creating it takes time, but verifying it, especially if you have intermediate checkpoints, is much faster. They like SHA-256 for its simplicity and proven security.
Okay, a verifiable time element. Now we have SPOA, proof of access, and VDFs, proof of time. How do they combine in succinct proofs of replications, SPoRes?
SPoRes is where it really comes together. It builds on SPOA to let a prover and Arweave miner convince a verifier, the Arweave protocol itself, that they are reliably storing a certain number of complete replicas of the dataset.
Not just proving access to one chunk, but proving they hold, say, 20 copies of the whole thing.
That's the goal, yeah. And doing it succinctly, with minimal communication. The paper calls it the SPoRes game.
Tell me about the game.
Okay, Alice the miner claims she stores N replicas. Bob the protocol wants proof. Bob gives Alice a difficulty level D and a random seed.
It's a VDF seed.
Right. Alice uses that seed and the VDF to generate those 1-second checkpoints we talked about. Each checkpoint potentially unlocks a set of COA challenges, locations within the packed data she should have.
If she has the N replicas she claims.
Exactly. If she has the packed chunk for a challenge, she generates the SPA proof. Then she hashes these proofs and compares the result to the difficulty D Bob gave her.
What happens if it meets the difficulty?
If the hash is greater than the difficulty target, it's a valid solution. She sends just that one small solution proof to Bob, the network, and Bob notes the time.
Okay, so it's like a continuous test. Keep finding these proofs.
Exactly. The difficulty determines the probability of any single SPOA attempt yielding a valid solution. If Alice has more replicas, more N, she can run more SPOA checks in parallel each second, increasing her chances of finding a solution quickly.
And Bob sets the difficulty.
Bob, the protocol, adjusts so that a miner who truthfully has N replicas should find and submit a valid solution on average every 120 seconds, 2 minutes.
The block time.
Precisely. If Alice consistently delivers proofs at that rate over a long period,
Right.
weeks, say, Bob gains incredibly high statistical certainty that she's not lying about holding those N replicas.
How certain?
The paper gives an example. After just 2 weeks of consistent proofs every 120 seconds, the probability of Alice actually storing fewer replicas than claimed becomes astronomically tiny, like 99.9997% certainty.
Wow. And this whole verification needs very little data transfer. Just that one small proof every couple of minutes.
That's the beauty of it. Highly efficient proof of ongoing replication. And the certainty increases superlinearly with time, independent of how big the data set gets.
That is genuinely ingenious. So how does this SPoRes game directly translate into Arweave mining and creating new blocks?
Arweave mining is essentially a network-wide SPoRes game. The protocol acts as Bob, setting the difficulty and seed. All the miners collectively play as Alice, racing to find the next valid SPoRes solution.
And the first miner to find one?
Gets to create the next block. That successful SPoRes proof becomes the cryptographic link securing the new block to the chain. The paper specifies the exact SPoRes parameters Arweave uses, factoring in the block index, the number of data partitions a miner stores, and the current network difficulty D.
And that difficulty adjusts automatically.
Yep, it recalculates regularly to keep that average block time steady at around 120 seconds, regardless of how much mining power joins or leaves the network.
The VDF difficulty for the 1-second checkpoints also self-adjusts.
So, miners are constantly playing SPoRes, competing to find proofs, and those proofs build the blockchain.
That's the core mining loop.
Okay, but the paper also digs into incentives for replica completeness. SPoRes proves you have some data, but how does Arweave push miners to store the whole data set, not just cherry-pick easy or popular parts? Excellent question. This is vital. The SPoRes system assumes rational miners acting on incentives. So Arweave modifies the basic SPoRes game slightly to strongly encourage storing all the data parts.
How does that modification work? What's the tweak?
It cleverly splits the SPoRes challenges unlocked by each VDF checkpoint into 2 sets.
2 sets?
Yeah. One set of challenges requires the miner to access data within just one specific partition or section of the overall Arweave data set. Let's call these local challenges.
Okay, challenges within one partition.
But the second set of challenges, unlocked by the same checkpoint, requires the miner to access data that spans across all partitions of the entire data set. These are global challenges.
So if a miner only has, say, half the partitions,
they physically cannot solve the global challenges because they don't have the required data pieces from the partitions they're missing. They miss out on the potential rewards from that entire set of challenges.
Got it. That directly penalizes incompleteness.
Exactly. The paper analyzes the performance per packed partition. It shows mathematically that a miner's potential reward rate, their hash rate contribution, is significantly higher if they store unique data partitions that contribute towards a full replica. Storing duplicate copies of partitions that are already common offers much lower performance.
So storing unique data needed for completeness pays better than storing duplicates.
Way better. There's a quadratic penalty, essentially, for not storing unique data as the total data set, the weave, grows.
And this leads to the idea of marginal partition efficiency.
Right. That quantifies the extra benefit a miner gets from adding one new unique partition versus just adding another copy of a partition they already have. The analysis shows this benefit is highest when a miner is close to completing a full replica.
So it strongly incentivizes miners to either get the full dataset themselves or maybe team up with others.
Precisely. It encourages cooperation, forming mining pools or groups that can collectively ensure they have access to the complete dataset to maximize everyone's rewards. It's a built-in incentive driving towards full data replication across the network.
Really elegant game theory design there. Now, can the network itself figure out how well it's doing? Estimate how many complete replicas are actually out there?
Surprisingly, yes. It can get a good estimate just by observing the blocks being mined.
How?
By looking at the ratio of successful SPoA proofs coming from those local single partition challenges versus the global all partition challenges we just discussed.
If everyone had full replicas, the ratio would be different than if many miners had incomplete data.
Exactly. If everyone was complete, you'd expect a certain ratio. If there's lots of incompleteness, you'll see proportionally fewer successful global proofs. The paper gives formulas to estimate the average replica completeness and overall mining efficiency from this observed ratio.
And from that, they can estimate the total number of partitions being stored across the whole network, and thus the total storage capacity.
Yep. All calculated just from data readily available on the blockchain itself. No extra coordination or reporting needed from miners. The network can monitor its own health and redundancy passively.
That's seriously cool. Okay, another incentive angle. Incentives to optimize data routing. Why is routing data efficiently so important here?
Because miners are so strongly pushed to get and keep full replicas, they have a massive self-interest in being able to access any piece of data from anywhere else on the network quickly and reliably.
They need data on demand to solve those SPoA challenges, right?
Exactly. If they can't get a required chunk fast enough, they might miss out on a potential block reward. This necessity creates a powerful downstream incentive for miners to develop really optimized peer-to-peer data routing solutions.
So the need to mine efficiently forces them to build better data highways within the network.
That's a great way to put it. And importantly, the routing infrastructure they build for their own mining needs can then also be used by regular users trying to retrieve data, or by other miners needing to replicate data.
Like the Bitcoin mining hardware race driving chip innovation, but here it's driving routing innovation.
That's the parallel the paper draws. Expect competition and innovation in routing tech specifically tailored for Arweave's needs.
So the mining incentives naturally improve data access for everyone. Makes sense? What about sharing the bandwidth needed for all this data movement?
Right. That need for data access creates incentives for various bandwidth sharing structures to emerge. The papers suggest a few possibilities.
Like what?
Well, you could have informal systems like Karma or optimistic tit-for-tat similar to BitTorrent. Nodes track who shares bandwidth with them and prioritize those peers, maybe with some random sharing thrown in.
Reciprocity.
Yep. Or for miners with really constrained internet, maybe even markets for physically shipping hard drives loaded with data chunks could emerge. Buy a disk full of the latest Weave data.
Sneakernet.
Exactly. And then there's the potential for more formal payment protocols built on top, maybe using payment channels, where nodes could directly pay each other for bandwidth or fast data access. P3, the Permaweb Payment Protocol, is mentioned as an example.
So market forces could shape how bandwidth is shared and paid for within the ecosystem.
That's the expectation, an organic evolution based on need and incentives.
Okay, this brings us to a huge topic for any permanent storage system: scalability. How does Arweave handle potentially limitless amounts of data being added over time?
Good question. We know Arweave has blocks every 2 minutes, and each block has a limit of around 1,000 transactions.
Which sounds potentially limiting.
You'd think so, right? But that transaction limit doesn't actually bottleneck the amount of data Arweave can absorb, thanks to a really important mechanism called bundling.
Bundling, what does that involve?
Bundling is essentially a standard, kind of like a layer 2 solution, built using Arweave's base layer. It allows you to package Many individual data items could be tiny files, large images, code, whatever, into a single Arweave transaction.
So instead of 1,000 small files taking 1,000 transactions, you put them all in one bundle transaction.
Exactly. And these bundled items are treated by the network. Just like top-level transactions, they get the same permanence guarantees. When someone wants to retrieve the data, the bundle can be easily unpacked back into its original items.
Is there a limit to bundle size?
The theoretical limit for a single Arweave transaction is astronomically large, 2 to the 256 bytes, and you could even put bundles inside other bundles recursively.
Nested bundles. Wow, okay, so how do these potentially huge bundle transactions get chosen to go into those 1,000 transaction blocks?
Selection is based primarily on the total value offered to the miner, basically, the transaction fees paid.
So a big bundle paying a decent fee might be more attractive to a miner than lots of tiny transactions paying very little.
Precisely. This creates a natural incentive for specialized bundling services to emerge. These services collect lots of smaller user uploads, bundle them together efficiently, and submit them as single, high-value transactions.
Effectively scaling the network's data throughput way beyond the 1,000 individual transaction limit.
Exactly. There's no hard practical limit imposed by the base protocol. It's a really elegant scaling solution.
And this is different from how some other blockchains handle scaling, like block space auctions.
Very different. Block space options can lead to really volatile and sometimes very high fees. In Arweave, the competition between these bundling services actually tends to exert downward pressure on the fees users pay. Bundlers compete to offer the best rates.
That's good for users. And bundling also allows flexibility in how users pay.
Yes, because the bundling can happen off-chain. Users can potentially pay the bundling service using various cryptocurrencies, or maybe even fiat, depending on what the service supports.
The user pays the bundler pays Arweave and AR.
Exactly. The paper noted at the time there were already like 18 different payment modes supported via bundlers.
Yeah.
Huge flexibility.
Okay, bundling seems key for scalability. Now let's revisit the storage endowment in more detail. We know you pay into it upfront. How does that financial engine really work to ensure permanence?
Right, so you upload data. You pay a small network transaction fee, plus that larger upfront contribution to the storage endowment, paid in AR tokens.
And this endowment is the pool of money that pays miners forever.
That's the goal. It provides the ongoing rewards to miners for continuously proving they're still replicating the data year after year, decade after decade. Crucially, the amount of payout needed per gigabyte per year is expected to decrease over time.
Because storage technology gets cheaper, the Kreiter rate thing.
Exactly. Moore's law for storage, essentially. The endowment anticipates this decline in cost.
So how does the protocol figure out the right upfront price to charge? Enough for 200 years? Or potentially longer, given falling costs?
It uses a really interesting trustless mechanism based entirely on observing the network's own behavior.
No central price committee?
Nope. It estimates the total amount of storage capacity currently being provided by all miners on the network. It does this by looking at the current network mining difficulty and the block rewards miners are earning.
Okay, estimates total supply.
From that, it calculates the implied current cost to acquire 1 gigabyte of storage for, say, 1 minute directly from the miners.
Based on what miners are actually earning.
Right. To smooth things out, it averages this calculated cost over the previous 6 weeks.
A rolling average cost.
Yep. That rolling average cost then becomes the basis for the user's upfront payment. Currently, the calculation aims to cover the cost of storing 20 replicas of the data for 200 years at today's estimated average cost.
Wow, okay, that's quite specific. And the endowment then pays out from this pool over time.
Yes, there's a formula determining how much AR gets withdrawn from the endowment, each block, to compensate miners proportionally for the total data they're proving they store.
And this whole pricing mechanism based on actual miner costs,
Yep.
It forces miners to compete on efficiency, right?
Absolutely. It creates intense pressure to find cheaper hard drives, more efficient cooling, better data center deals, anything to lower their actual cost of storage below the network's calculated average cost. Very similar to the Bitcoin hash rate competition driving hardware innovation.
So competition keeps costs honest and drives them down. What about the endowment and the AR token itself?
When you contribute AR to the endowment, those tokens are essentially locked away, removed from the active circulating supply. They form this dedicated reserve for future storage payments.
Okay.
The purchasing power of this endowment is elastic. right? Depends on how much data needs storing, what the actual cost of storage is at any given time, and of course the market value of the AR token itself.
And the Kreider plus rate, the rate storage costs fall, is key here.
Hugely key. The protocol's math is designed so that if storage costs fall by just 0.5% per year, which is extremely conservative historically.
Right, you said history shows like 38% decline.
Exactly. So even with just a tiny 0.5% annual cost decline, the endowment can theoretically sustain payments forever without any need for the AR token price to increase.
Wow.
Given that historical decline rate is much higher, it creates a massive safety margin. It means the endowment can weather volatility in AR price, and potentially, over the long run, if uploads continue, it could even lead to the AR token supply becoming deflationary as more tokens get locked in the endowment than are paid out.
That's a fascinating economic model intertwining tech progress and tokenomics. Okay, let's shift gears slightly. Content policies. How does a decentralized permanent system handle problematic content, illegal stuff, abuse material, etc.?
This is obviously a critical and complex issue for any open platform. Arweave uses a layered approach fundamentally based on voluntarism. There's no central censor.
Layered, what are the layers?
First layer, the miners themselves, the people actually running the nodes, storing the data. They can individually choose to run software that filters content they deem unlawful or maybe just objectionable according to their local laws or personal standards.
So a miner in Germany might filter content illegal there, but a miner elsewhere might not.
Potentially, yes. It's their node, their choice, subject to their local legal obligations.
Okay. Layer 1 is miner choice. Layer 2.
Gateways. Most users don't interact directly with Arweave nodes. They go through gateways, which are basically access portals. These gateway operators can also implement their own content filtering policies. They decide what data they want to index and make easily accessible through their portal.
So users can choose gateways that align with their preferences.
Exactly. You might have gateways with very strict filtering and others with almost none. User choice.
And layer 3.
Applications. Developers building apps on top of Arweave can implement yet another layer of filtering specific to their application's purpose or community standards.
Like a social media app on Arweave could filter certain content within its own interface?
Precisely. And these app-level policies could even be stored immutably on Arweave itself, so users can see exactly what rules an application enforces before they use it.
So it's distributed responsibility and choice, not a single hammer coming down.
That's the design philosophy, allowing diversity of policy through layers of voluntary action, rather than trying to enforce one global standard at the base protocol level, which would likely be impossible anyway.
Interesting approach. Okay, finally, let's talk about the very long term. Protocol evolution. How does something designed for permanence change? How does it adapt without breaking its promise?
Yeah, this is maybe one of the most philosophically interesting parts. The creators knew that true permanence requires adaptability. Technology changes, needs change, threats emerge. A static system might become obsolete or insecure over centuries.
But changing a blockchain is hard, right? Governance issues, forks.
Exactly. Traditional blockchain governance often struggles to balance adaptability with user guarantees about stability and immutability. Arweave proposes something different, an improvement on simple forking.
What do they call it?
They describe it as incentivized evolution, operating within a kind of constitutional social protocol. It allows the underlying technical protocol to mutate and improve over time, but in a structured way that respects user rights and the core principles laid out in documents like the framework and principles stored on Arweave itself.
Okay, how does this incentivized evolution actually work?
The core idea is to enable and reward permissionless innovation through a fork-like mechanism, but with better coordination incentives.
So anyone can propose an upgrade?
Pretty much. An innovator takes an existing version of the protocol, creates a mutated version with new features or fixes, and then offers it to the network. Often, they'll mint a new associated token as a reward or incentive for nodes and users to adopt their improved version.
And the community decides?
Essentially, yes. Miners, users, developers evaluate the proposed changes. Is the improvement worth adopting? What's the impact of the new token distribution? Dilution. The goal is for the network to naturally select evolutions that maximize its overall fitness utility, robustness security, while minimizing disruption.
Like natural selection for protocol features.
Kind of, yeah. A marketplace of ideas where the best adaptations hopefully win out over time.
Are there incentives for innovators to cooperate with existing versions rather than just creating totally separate competing chains?
Yes, strong ones. By building on an established Arweave version, innovators can easily bootstrap adoption, inherit the existing user base and data, and become part of the recognized lineage of permanent storage. It's usually much easier than starting from scratch. This open, incentivized mechanism makes participation more attractive than pure competition for most innovators.
What about the data stored on older versions if a new evolution takes off? Does it get left behind?
That's a key concern, but the system has powerful incentives for dataset unification. Meaning, it's usually in the innovator's best interest to include the data from prominent previous forks when they propose a new evolution. A unified protocol that contains all the previous data is almost always more valuable and attractive to users than a fragmented one.
So innovators are pushed to merge the history.
Strongly incentivized to, yes. They'd address any technical compatibility issues and make sure the data from significant diverging forks is accessible in their new version. This encourages users to migrate confidently.
Is there a way to quantify that incentive?
The paper actually presents a rough formula. Basically, it weighs the potential market cap gain from unifying data against the cost of doing so. Since the cost of just copying the data, DC, is usually tiny compared to the potential market value gain from including a prominent force data, FM, the incentive V to unify is typically very strong.
V, FMCD, FMCN, DC plus DV, something like that.
You remembered the variables. Yeah, the point is, the math usually pushes strongly towards including existing data.
So users can be pretty confident their data uploaded to a major Arweave network will be carried forward in future evolutions.
That's the conclusion, yes. High confidence. And existing AR token holders might even find they accrue value or tokens across different evolutions, while everyone benefits from a protocol that gets better and more robust over time.
A system designed to balance permanence with progress. Really fascinating stuff.
It really is. A very deliberate attempt to engineer for the extremely long term.
Well, that was certainly a deep dive. We've really covered a lot of ground today. To quickly recap for everyone, Arweave's mission for permanent information storage.
Its unique take on decentralized consensus using proofs of storage.
The clever economic incentives driving replication and efficiency like the endowment and mining rewards.
And that really unique approach to long-term protocol evolution and governance.
Our goal here was to give you, the listener, a solid grasp of the core technology and the thinking behind Arweave without getting totally lost in the weeds.
Yeah, hopefully you have a clearer picture now. It's a complex but genuinely innovative project tackling some fundamental digital age problems.
Absolutely. Which brings us to our final provocative thought for you to mull over. What are the long-term implications if we actually achieve a truly permanent, globally accessible, uncensorable layer for human information?
Right. What becomes possible for knowledge, for culture, for history, when information doesn't just fade away, when it can truly last?
Big questions, definitely worth thinking about. We'd encourage you to explore the Arweave network itself, see the ecosystem that's growing on top of it.
Check out the applications, see what people are building.
Thanks for joining us on The Deep Dive.